All right. Hello, everyone. Welcome back to the Origin seminar. Before I introduce our speaker, just a brief reminder, hold your questions until the end of the talk. If you have a clarification question that cannot wait, you can put it in the chat and then one of the organizers will ask the speaker. All right, so today's speaker is Dr. Jaehan Bae. Jaehan got his PhD from the University of Michigan, working with Lee Hartman. He then went to the Carnegie Department of Terrestrial Magnetism as a Vera Rubin postdoctoral fellow. And he has stayed on at Carnegie now as a Sagan postdoctoral fellow in the New Earth and Planets Lab. He is an expert on computational simulations of disk dynamics, which he's going to be telling us about a bit today. Jaehan, the floor is yours.
Okay, thanks so much. Let me share my screen. Can you all see it?
Looks good.
Great. Yeah, thanks for the introduction and thank you for the organizers for having me today, and thanks for joining everyone. So I'll be talking about planet disk interaction, and of course we are in the era of high resolution observations, and in particular I'd like to highlight today that thermodynamics of disk can be very important to interpret these gorgeous, incredible observations. So I'd like to first thank my collaborators, in particular Rich Teague and Jaehan Zhu, and also MAPS collaboration. Okay, so I'll start by showing this kind of obligatory image these days in disk talks, right? This is an ARMA survey, D-sharp survey. So you're looking at millimeter continuum images of 20 protoplanetary disks. And you can see that there are a whole bunch of substructures in this particular image set of images. You can mostly see gaps and rings, but you also see some spirals as well as vortices. And in a separate slide, I compiled some of those images with spirals because I'll be talking a little bit about spirals today. So the question is really what forms these substructures, right? So there are many possibilities, of course, but planets can offer an exciting explanation. And I'd like to highlight that gaps and spirals, we see those substructures again, right? But those are two most fundamental outcome of planet disk interaction, as you can see from this 3D simulation with a Jupiter mass planet. Now, if we believe that these substructures are formed by planets, right? There's a big if, of course, but then what you can do is you can try to reproduce these observations by running numerical simulations and also some post-processing radiative transfer calculation. And what I have done here is these are some observations, for example, SAO 266462, which shows this grand design two-armed spiral. This is the famous image of HL tau. You see set of rings and gaps, and this is showing a specific line channel map where you see this deviation from Keplerian rotation, which we can interpret as a kinematic signature of planets. Now, what I have done on this diagram on the right-hand side here is I plotted masses, planet masses, as a function of semi-major axis in log scale in units of Jupiter masses on the y-axis and in units of astronomical units on the x-axis. And with gray dots, these are all confirmed exoplanets, right? And with black squares, I'm showing you the solar system planets. And all these color symbols, what I have done here is I collected data from literature where we as a community try to reproduce these observations. So for example, if you look at any specific data point, what it tells you is that you may need certain mass of a planet at certain location in that disk to reproduce these observations. And there are many disks showing signatures of planet embedded in their protoplanetary disks. So it's very interesting because we are essentially probing the primary space where we don't have much exoplanets, right? We are limited to close in and mostly massive planets. If you look at exoplanet, multiplanet population, but we are specially limited to look at those inner 10-ish AU in protoplanetary disks. So that's why we have a lot of data points on this side of diagram. And now then you can ask very interesting questions about planet formation and evolution, right? If these are real planets and they have these mass and semi-major axis, how would they evolve over the next million years or billion years, right? Would they stay there as a cold icy giant, or would they migrate inward and become hot Jupiter or cold Jupiter? And while they're migrating in, they may lose some of their atmosphere and become super Earth or mini Neptune mass planets. So that's an open question. We don't have an answer to that, but it's certainly interesting to see that we are probing a distinct region with respect to exoplanets. Before I move on, I'd like to advertise this review paper we wrote after a workshop last year, where we gathered and discussed about the possibility of using ALMA kinematics line observations to find signatures of planets. So it is now in the archive as of last month. And we got a lot of good feedback from the community. And one of them was that I was asked to provide all the data points that I used to make this diagram. So here we go. That's the table showing you the disk name, planet masses, semi-major axis, and the method used in each of these papers. E means that they have used empirical relations between the planet mass and, in this particular case, the width and or depth of the gap they observed. And F means forward modeling. So they ran numerical simulations and or radiative transfer calculation. So you can take a screenshot and follow this link, GitHub link. And if you go there, you will find these files. I have the same figure in PDF or PNG, so please feel free to use. And in this TXT file, I have all the numbers, masses, a disk name, and the references where I got those numbers from. So yeah, have a look if you're interested in, and if I missed anything, I'm sorry, but please let me know, because there are so many observations these days, and it's not impossible that I missed many of those recent ones. Okay, so going back to the science. Okay, so I told you that this is very interesting regime, right? Reason in this parameter space, but now you may want to ask how reliable our estimates are, right? I can tell that, well, those shouldn't be like Earth mass. Those shouldn't be, more than brown dwarf mass regime, right? But how accurate are we in estimating these planet masses? So I'll go over a few items. These are what I'm going to focus today in my talk. So the first is, of course, the degeneracy among parameters. We want to know the planet mass, but we are not sure about this temperature and or viscosity. I'll get back to each of these points in a minute. And thermodynamics. And in particular, I'd like to ask if the isothermal assumption is good enough, or should we really avoid using isothermal assumption in numerical simulations? And lastly, two-dimensional versus three-dimensional simulations. Or you can think of, from the point of view of observation, you can think of this as continuum versus line observations. But other than these three, actually, there are a lot more complications. For example, one planet can open more than one gap. And also, when a planet opens a gap, photochemistry, thermochemistry inside the gap, that can change the gap shape, so depth and width. So that's a big thing. Of course, we do expect that magneto-hydrodynamic effects will be more significant when there's a gap. And also, we often assume that planets are in a circular orbit, a circular fixed orbit. But when planets start to migrate, and when planet has non-zero eccentricity, it can greatly change the shape of the gap. So they all matter. Now, going back to this, the three factors that I'd like to mention today. the degeneracy, right? So this is a plot from one of the teacher papers where they have ran a bunch of simulations. This is two-dimensional isothermal simulations, by the way, where they vary the disk temperature or disk aspect ratio, H over R, in this column, right? And then along each column, you see different alpha values. So that's viscosity. And with different colors, you see different planet masses. So when you do that, right, you can then measure the width of the gap, and then you can make this plot. This is the gap width on the y-axis, and on the x-axis, you have this dimensionless parameter K prime, which is a function of planet mass, Q, disk aspect ratio, or disk temperature, and this alpha here is this viscosity. So what you want to know from observation is you measure the gap width, right? And then you want to know the planet mass, but you need to know the disk temperature and disk viscosity to get accurate planet mass. So there's that degeneracy. Now the second one is the thermodynamics. So these are two papers published earlier this year where they looked at the cooling time scale of planet disk interaction simulations. So oftentimes we run planet disk interaction simulations using isothermal equation of state. So that's what is presented in the left panel. So when you use isothermal equation of state, here's the planet at one radius. This is radius, by the way, and this is azimuth, so R phi. So the planet excites spirals, as you can see, right? But now what they have done here with different TC is, TC here is, by the way, cooling time scale normalized by dynamical time scale. So when you have TC of 0.01, what that means is that the cooling time at each location of the disk is 1% of orbital time scale. When you have 1, the cooling time scale at each location of the disk is same as the dynamical time scale, right? So you can think of short cooling time scale to be more isothermal and longer cooling time scale to be more adiabatic, right? And as you can see, when you vary that cooling parameter, you see that spiral shape and strength can change drastically, especially when the cooling time scale is about 0.1 or 1, right? You can immediately see that those spirals are much weaker than the other cases. On the right-hand side, this is pretty much the same simulation, isothermal, different beta. Beta is the same as TC on this left plot. And you can see here what they plotted here is the surface density as a function of radius. So planet is at 1, and in isothermal simulation, spirals open gap at different locations, but as you move to longer cooling time scale, what happens here is that linear cooling through radiative damping becomes very important near the planet, and that's why you open a gap immediately next to the planet, and you open a single gap around the planet. So this is very different. And I'd like to note that this effect of thermodynamics is not yet taken into account the empirical relation that I showed in the previous slide. And this is some observational implication of how thermodynamics can matter in interpreting observations. This is one example of Lukashian 15. By the way, this is the disk that we talked about 2 weeks ago by Josh Eisner. This is the same disk looked at millimeter wavelength. So this is actual data. You can see the inner big cavity where we might have giant planets. And if you look at the outer disk, you see this bright ring and gap and another ring and tenuous emission beyond, right? Now what I have done here is I ran numerical simulations with different thermodynamics, isothermal simulation, beta of 1, beta of 100, and I used everything the same, disk model, planet mass, stellar mass, everything, but I varied the cooling time scale in the simulation. And I put a planet at this location on the sky, and what you see here is as you vary the thermodynamics, the cooling time scale, you can vary the appearance of the disk very significantly. For example, in this case, planet is embedded in the middle ring, and you open multiple gaps and rings. In this case, beta equals 1, the planet is embedded within the continuum gap, and you see two continuum rings. And when beta is 100, you don't see any particular signature around the planet, which is actually in good agreement with our previous studies. So this is showing you why it is important to use correct thermodynamics or correct cooling time scales. And also, we have been running a lot of two-dimensional simulations, and that is, of course, good to explore large parameter space. We want to vary planet mass, this temperature, this viscosity, and on top of that now thermodynamics. So that's a good point, and it is reasonable. It takes reasonable computational cost, but of course, it is not ideal if you want to compare molecular line observations. For example, 12CO, which we know that they are optically thick and they are not probing the mid-plane region. And also, with two-dimensional simulations, we cannot capture three-dimensional physics or phenomenon. For example, meridional flows, spiral wave instability, buoyancy resonances. I'm going to talk about buoyancy resonances in particular later in my talk. So here's the outline of my talk. So I will discuss a little bit about the thermodynamics and discuss how that may impact the estimation of planet mass. And for the next, I'll discuss what is then beta or cooling time scale in protoplanetary disks. And last of all, I will introduce these buoyancy resonances. So to begin with, what I'd like to do is to explore this planet mass, this temperature, viscosity, and thermodynamics, this parameter space, but using 3D simulations. But as I said, doing this in 3D is very challenging because of the computational cost, right? But we know that disks are three-dimensional objects. This is a cartoon version where you see the star and the disk is puffed up. It's not just infinitely thin. So small particles are puffed up, large grains are settled down near the midplane. And this is what you see with VLT observation of IM loop disk. You can see the upper surface. So those are, we are basically seeing photons emitted by the central star and then scattered off the emission surface toward our line of sight. And you see the opposite side, far side of the disk in the middle, because they are not getting stellar photons directly, we see this dark lane. That's where midplane is located at. And with ALMA, this is now ALMA data at millimeter wavelengths, and you can see the millimeter continuum disk. And you can see that the geometry that we see is very different. You are looking at a flared disk with micrometer observations, whereas you are looking at basically a flat, two-dimensional, almost two-dimensional pancake-like disk with millimeter continuum. Now, ALMA can do more than this, right? So we can look at various transitions or molecules with ALMA, and this is what we get for 12 different molecules and or transitions. So by doing so, by using these line observations, we are basically scanning disk in 3 dimensions. This is great because now then what you can do is you can infer the gas temperature at each location of the disk as a function of radius and height. So this is the result for HD16396. And you can see the radial and vertical gradient. You see hotter temperature near the surface. That is because you are directly heated by stellar photons. And I just wanted to mention that in this plot alone, we have more than 4,000 data points. So it's a lot of data. And when you have that information, you can try to fit the temperature in R and Z, and you can then use this temperature from observation for your numerical simulation, right? And in some disks, we can get a pretty good sense of level of turbulence. This is one example from Kevin Flaherty. And you can see that you can measure the line width of different molecules and see how much non-thermal motion exists in the disk. And you can put some strong constraints on the level of turbulence. So essentially what you can do now is, if you look at a particular disk, you have good measurements in line observations, then you can remove this temperature and this viscosity dependency, and you can explore only the planet mass and thermodynamics. So that's what I have been trying to do. So I am focusing on HD 163-96. If you have been following this community, this is the velocity kink. So if you look at this side of the disk, you see this light bolt shape emission, whereas the other side of the disk, you don't see that feature. It's smooth. So we interpret this as a signature of a planet perturbing a disk locally. So I am looking at this particular feature, and also gap width and depth and velocity structures, how they vary as a function of planet mass as well as the cooling timescale. So this is work in progress, but here's some preliminary research where I ran three-dimensional simulations, again, adopting the temperature constrained by ALMA line observations and viscosity also constrained by ALMA line observations. And I varied beta parameter, the cooling timescale. So this is quick cooling, intermediate, and long cooling. So you can think of isothermal to adiabatic in this direction. And here I put a 2 Jupiter mass planet and 240 AU. That's the estimate that Christoph Pint gave in his paper. And you are looking at the disk surface density evolution. And you can immediately see that the gap depth and width is very different between the three simulations. And this is the radial profile of the disk in gas density. And you can see that the gap, here's the planet, 1, 2, 3 scale heights in radius, plus minus. And if you compare different colors, if you look at isothermal simulation, that's the black, underlying black color here. And when you assume beta of 0.01, 0.1, you can see that they are close enough to isothermal simulation. But when you increase beta parameter 1, 10, 100, you see that the gap structure started to deviate from the isothermal simulation. Now you can use rotation velocity to measure the gap depth and width, and this is what we have done in Richtig's 2018 paper. So when you have a gap like this, the disk will rotate slightly different from Keplerian velocity to maintain the radial force balance. So you expect to see sub-Keplerian rotation inside of the peak of the gap and super Keplerian rotation outside of the gap center, right? And this is what we actually got for HD 163-96. This is the rotational velocity, and where we subtracted the Keplerian velocity. And along the lines where I indicated the location of continuum gap, where we believe that there's gas gap at these locations, right? You see exactly the same pattern that we expect from this view, right? So sub-Keplerian to super-Keplerian rotation, again, sub-Keplerian to super-Keplerian, and the same. And this is the last one where CEO velocity kink is observed at 240 AU. So from the simulation, what I have done is I measured the width of the gap between the velocity peaks and also the depth. And this is the result. So I varied beta parameters, so isothermal simulations, small beta to large beta. And on the y-axis, what you see is the gap width in units of AU, astronomical units. On the right side, you see gap width in units of scale height at the location of the planet. So when you assume isothermal simulation or a very small beta value, you see pretty much constant value of 100 AU for the gap width, right? But then as you saw in the simulation movie, when you increase beta to 1 to 100, the gap shape changes a lot. And the width of the gap measured using the rotational velocity is almost factor of 2 smaller than the isothermal value. It's only 50 to 60 AU, right? And this is a work I have done with my PhD student last year. What we have done is we measured rotation velocity, and from simulation, this is, by the way, 2D isothermal simulation, and we measured the gap width using rotational velocity. And what we have plotted here is the width of the gap as a function of planet mass. So in the x-axis, the planet mass is normalized with thermal mass. You can think of it as gap opening mass to the first order. So you can interpret this side. This is pretty straightforward. As you increase your planet mass, your gap width is increasing. That's straightforward. What's happening on the other side when you decrease from one thermal mass to smaller mass? What's happening is that the spirals that the planet excites do not shock the disk immediately, but they have to propagate in radius, and that's why the gap is broader than otherwise. So we got a minimum of gap width, which is about 4.5 times scale height, and that's going to happen at about thermal mass. And in this case, we can see that pretty clearly when we assume isothermal equation of state, we get this width of about 4.5 times scale height, which is in good agreement with this two-dimensional simulation. But then when the thermodynamics is different, then the gap width can be very different again. Now, if you look at the data, 12CO data of HD 16396, and if you look at this particular one, if you see this sub-2 supercapillary rotation change, the width of this gap is about from 210 AU to 260 AU. That's only like 50 AU or 2 scale heights. So if you were to explain this gap using isothermal simulation, it's really hard to reproduce this narrow gap, right? And you really need some larger beta value. And this is now gap depth measured in meters per second. So from isothermal simulation to adiabatic simulation, one thing to note is that depending on where you measure the velocity difference, this is z over r of 0.3. That's where approximately where 12CO is tracing. Z over r of 0.05. This is 13CO is tracing. Z over r of 0. That's the middle plane. Depending on where you measure, you get different values, and it's a function of beta value, right? But if you look at the midplane, regardless of what value you use in your simulation, you get pretty much constant velocity depths, gap depths. So what that tells you from observational point of view is that we may want to look at the midplane using optically thin lines to break this degeneracy between the beta and planet mass. So far I talked a lot about beta, right? Using beta value of something or something, right? But what is beta in protoplanetary disk? Or what is the cooling time scale in protoplanetary disks, right? So if you think about how gas cools, right? Almost all the thermal energy and mass is in hydrogen molecules in protoplanetary disks, right? But we know that they are very poor at emitting radiation, right? So what they have to do is that they need to collide with those particles, and then subsequently those particles either radiate away the thermal energy, excess thermal energy, or if it's optically thick, you can think of this as a diffusion process, as radiative diffusion. So what I have done here is I built a disk model. This particular one is for TW Hydra for a reason I'll explain later. As a function of radius, what I have done is I distributed those particles in 3 dimensions, assuming level of turbulence characterized by alpha of 10 to the minus 3. So as you can see, you have larger grains in the inner disk near the middle plane. You have smaller grains near the surface, which makes sense, right? What you can do is then you can compute the dust to gas mass ratio in each of those degrees. And near the middle plane, you have about 0.01, which we typically assume. But as you go up, because those particles are settled down to the middle plane, you get dust to gas mass ratio of 10 to the minus 3, 4, 5, 6, 7, which is pretty small, right? So what does that mean? If you look at optically thin region, you have your hydrogen molecule. It collides with a dust particle, And because it's optically thin, those particles immediately radiate away the excess thermal energy. So this is one-time process, right? So the time scale for this radiative cooling is very short in the entire disk. It's orders of magnitude smaller than the dynamical time scale. Now, if you move to the optically thick region of the disk, now this has to happen multiple times. The dust particle radiate away excess thermal energy, but then it is observed by nearby grain, right? And then it has to be re-emitted and observed again, emitted again until you finally escape the disk. So it takes a while. And if you do the math, what happens here is you need about orbital timescale or dynamical timescale or longer in the inner disk region near the midplane, and that is because you have a lot more material, a lot more dust particles there, right? But if you go up again, you get less and less, shorter and shorter diffusion timescale. Okay, so there's that. But what is the collisional timescale, right? You need to first collide with dust particle. Now you can compute the collisional timescale because you know what the number density of your hydrogens and what the number density of dust grains, right? This is basically showing you the number density of the dust grains. And as you can see, dust mass or dust number density exponentially decreases as a function of height, and that's what you see here. So near the midplane, the collisional timescale is about order of orbital timescale or dynamical timescale. But as you go up, z over r of 0.123, as you go up, your collisional timescale is exponentially increasing, 100,000, 10,000. So what that means is that the cooling of hydrogen molecules is limited not by radiation or radiative diffusion, but near the surface, the cooling is limited by the collisional rate between gas molecules and dust grains. And if I combine all these three, radiation, radiative diffusion, and dust gas collision, this is the cooling timescale that you get in the end. So if you look at this gray region near the midplane in the inner disk, that's where the radiative diffusion, this one becomes important. Everywhere else, the cooling timescale is limited by the gas and grain collisional rate. So of course, this is just one model. So you can ask, what if you tweak your parameter, right? So this is the standard model that I just presented, and I varied different parameters. This is diffusion length scale. This is alpha parameter, which basically dictate the scale height of the dust particles in this particular case, maximum grain size, particle size distribution, disk mass, and when you have a gap opened by a planet, and you can see that you can tell that it's green, orange, yellow, red, which means that the cooling time scale is order of dynamical time scale or longer. By the way, I'd like to point out that this is not the first time we realized that. This has been known, and this is one example from Maligin 2017 paper. This may look a little bit different because they plotted z over h, the scale height, whereas I used z over r. And also they use logarithmic scale for radius, and I use a linear scale. But if you look at, say, 100 AU, and you go up to 3 scale height, the cooling time you get is very long, longer than the dynamical time scale. So we have been knowing this for a while, but this hasn't been really taken into account in planet disk interaction simulations. We often use isothermal assumption, or in some cases we take into account radiative cooling, radiative diffusion, but not gas grain collisional cooling. So I was asking if this is a problem and what happens when the gas dust collision limited cooling is considered in numerical simulation. And the answer is, yeah, it can be a problem. And why is it? We can miss some interesting physics. And one example here I'd like to share today is the buoyancy resonance. So again, disks are three-dimensional structures, three-dimensional object, right? And if you perturb a gas blob vertically in this example, you can expect that they will oscillate vertically with a frequency that is characterized by buoyancy frequency, right? And then now your gas is oscillating like this. And if there's a planet, right, orbiting around the central star, and if the orbital frequency of the planet and this buoyancy frequency match with each other, what happens is that this oscillatory motion is amplified due to the planet. And this is what I meant by buoyancy resonance. And I'd like to point out that, well, it makes sense, but we need some thermal requirement because we don't want the gas parcel cool too quickly before you meet the planet the next time. So cooling time scale has to be longer than 1 over buoyancy frequency. So now in this simulation that I will show, I included only radiated cooling and radiated diffusion. So you can tell that the cooling is pretty quick, except the middle plane and the inner disk. So here I put a 0.5 Jupiter mass planet at 90 AU in the disk, so in the middle of each panel, and I'm showing you perturbed density, perturbed temperature, and this is vertical velocity. And if I let it go, what you see is you have a planet and it excites inner spiral arm and in the outer spiral arm through Lindeblad resonance. And this is pretty much what you see every time when you see planet disk interaction simulation, right? Now, in the next simulation, I included all these 3 cooling. So the overall cooling is limited by gas dust collision, except near the middle plane and the inner disk region. And I'm going to show you the same movie, but as you will see, the planet excites inner and outer spirals through Lindeblad resonance, but all the other very tightly wound, these ones, they are driven by the buoyancy resonance. And they can be very strong. This is 0.5 Jupiter mass planet, and the perturbation that you see here in terms of sound speed, it's greater than 10% of the sound speed, which we can observe with ALMA, as I will show in a minute. So side-by-side view, this is when you just assume that gas and dust are thermally coupled. So cooling is very rapid. And then what you see is just 2 spiders, one in the inner disk and one in the outer disk. Now this is when cooling is extended because gas-dust collision can limit the cooling of the disk gas. So you see a lot more very tightly wound spirals. So one of the motivations that I started to think about this is because of this gas observation of TW Hydra. On the right panel, what you see here is the velocity of CO line, but the Keplerian velocity is subtracted. So you see only the perturbed velocity on top of the Keplerian. And you see these almost annular structure, red shifted and blue shifted structure, but those are not exactly annular, but their pitch angle is pretty small, less than 10 degrees. And it's really hard to explain those very small pitch angle or very tightly wound morphology with Lindeblad resonance. So I spent a lot of time, but it was really hard to reproduce this observation. But with buoyancy resonance, this is the vertical velocity. I'm showing you vertical velocity because TW Hydra is almost face on, and also buoyancy resonance generate predominantly vertical perturbation. So you see that all these red and blue very tightly wound spirals, those are due to buoyancy spirals, buoyancy resonance. And we made 12CO simulated image and ran through the simulator. And this is what you get after subtracting the Keplerian motion. And you can see that there's a set of red and blue shifted very tightly wound spiral, which look pretty similar to what we observe in TW Hydra. And again, the pitch angle. So the planet is at 90 AU. The 90 AU planet excites Lindeblad spirals, but they have very large pitch angle. Those symbols, diamond and square, that's what is measured in the simulation. They are very large and it is well known. And that's why I was not able to explain these spirals with Lindeblad resonance. The blue dots here near down here is what is measured from CO observation in TW Hydra, and the red symbols, they show the measured buoyancy spiral pitch angle from the simulation. So qualitatively, you can explain these very tightly wound morphology very well with those buoyant spirals. And in addition, I'd like to show this VLT sphere image of TW Hydra. And there are, of course, a lot of structures in the inner disk, but I'd like to highlight this gap here seen in micrometer wavelengths, which is at about 80 to 90 AU. So it makes perfect sense to me that there's not a planet inside this gap. So the planet might be responsible for this gap as well as the spirals we see with ALMA. Okay, so before I stop, I'd like to mention that buoyancy resonances, they can play an important role in orbital migration of giant planets as well. Well, giant planet as well as smaller tertiary mass planets too, actually. This is a very nice paper by Colin McNally, published earlier this year, where he showed the torque computed in 3D simulation where they set up in a way that buoyancy resonance does not operate in the simulation domain. And what you see here is that the torque due to the Lindeblad spirals, right? In the upper panel, what you see is that similar plot, but for a 3D simulation where buoyancy resonances operate. So you can see Lindeblad torque similar to the other one, but all the wiggles here you see, as well as these hot spot and cold spot, those are due to the buoyancy resonances. So if you measure the torque over time, what you see here is the orange here is when you don't have buoyancy resonances in the disk, right? This is two-dimensional simulation, by the way. And in three-dimensional simulation, when you have buoyancy resonances operating, the torque is greater in negative sign than the two-dimensional case. So it can affect the migration of planets as well. Okay, so I went through various things, but the takeaway points from my talk is, if you want to take just one thing, that you can remember that thermodynamics can play an important role in planet disk interaction. And specifically, the gap opened by a planet can be significantly narrower and shallower when the cooling is slower. Also, what that means is that if you are interested in estimating the planet mass responsible for disk substructures, then planet masses can be underestimated if you use isothermal equation of state. And I showed that the cooling of the disk gas can be limited due to infrequent gas dust collisions, especially in the surface layers, Z over R of 0.1 or larger, and also outer disk regions beyond 10-ish AU. And what this means is that the slow cooling can provide favorable conditions for buoyancy resonances to develop. And as I showed, you can expect to observe buoyancy resonances in line observations using ALMA, preferentially in face-on disks like TW Hydra. So I'll stop here and take any questions. Thank you.
All right, thank you so much, Jaehan. So it looks like we have a question from Andrew Uden.
Andrew, you're muted.
Thank you. That should be better. Jaehan, great talk. Thank you.
Thank you.
So at the end, I was interested, you seem to be showing that the migration was a fair bit noisier without the vertical buoyancy case. Is that just a 2D, 3D difference, or is there something more?
Are you specifically mentioning this one on the left side?
So just the torque versus time between your
Yeah, right.
orange line and blue line. Blue line is a lot smoother.
Yeah. Right. Yeah. I don't have an answer for that. Why 2D has more wiggles than 3D? Yeah. Yeah, I'll have to look at the paper again to answer that question.
Okay.
Yeah,
And
sorry
I'm
about
watching
that.
with, sure, yeah. And I'm watching with Caitlin. I think she has a question as well.
Is that okay, Camber? Can I go?
Oh yeah, sure.
Okay. So my question is on the simulations you did with you said the observationally motivated temperature profile and then the beta cooling prescription.
Right.
I'm wondering sort of to what extent those remain in steady state, because presumably you picked some initial temperature profile, and if you change the beta cooling by 3 orders of magnitude, the temperature structure in your disk is also evolving. So I guess, how do you reconcile interpreting those simulations if they are in fact way out of steady state?
Yeah, so, well, the way I took is, well, the maximum number for beta I chose is 100. So what that means is that when you have a perturbation, it will smooth out over 100 orbital time. So if you can run your simulation more than 100 orbital time, say you run 500 orbital time or 1,000 orbital times, then, well, of course, instantaneously, there's a very different change in temperature or disk structure.
Sure.
But if you run the simulation long enough over whatever you choose for beta, then yeah, that effect will smooth away.
But I guess, isn't the temperature structure of the beta equals 1 and beta equal 100 disk very different by the time you're doing this comparison of the gap depth and width, because they are either because because of how much cooling has occurred?
Well, again, yeah, it can be very different. It is indeed different when you look at the very beginning of the simulation. But when you compare those temperature at 500 orbit, 1,000 orbit, the difference is not very great, very much.
So I guess I mean, but if cooling affects the disk temperature structure, how is it that things with very different cooling rates end up having the same temperature structure?
Neil is chiming in on this.
Right, so Neil is asking, do the different beta runs all cool towards the same background temperature profile?
Yeah, that is correct, through thermal relaxation. That's why I was talking about, yeah, so you have initial temperature, and we assume that is a equilibrium temperature. That's why
see.
you
So
need
beta is explicitly T minus T background.
Initial, yeah.
Oh, okay.
Yeah, sorry about the confusion.
Yes. All right, we have a couple questions in the chat. First from Neil Turner, who says, thanks for covering several interesting effects. Can you comment on how the disk's internal thermodynamics could interact with stellar illumination and shadowing? And then he also, just to follow up on the last question, says, with beta much greater than 1, do you ever cool back to the background profile? So if you want to do that one first, then we can go back to his first question.
Okay, yeah, internal thermodynamics could interact with stellar illumination. Yeah, definitely. In this simulations, so you can think of it this way. So the stellar illumination is already taken into account if you observationally estimate the gas temperature, right? Shadowing is a little bit tricky because when you open a gap, it changes the density structure greatly. You can, for example, in this case, you can decrease the density by about an order of magnitude within the gap. And the shadowing, yeah, that can change the stellar illumination greatly and temperature structure. That one is not taken into account in this simulation. So ideally, what you want to do is you do ray tracing, radiative hydrodynamic simulation using and adopting some prescribed or real thermodynamics, radiative diffusion, and gas grain collision if you can do it all together. But I guess at least at the moment, it's too expensive to do that numerically. But yeah, when you change disk structure substantially, yes, stellar illumination and shadow can matter. Yeah, I see Andrea found Jupiter's gap could, yeah, sure. Yeah, I am aware of that. Yeah, it can change the temperature profile. And beta with greater than much greater 1, do you ever call back to the background profile? Yeah, as I answered to Caitlin's question, if you run simulation much longer than the beta value you assume, it does not go back to exactly the same temperature. What I found is that the overall disk temperature increases about 10 to 20% perhaps, but it doesn't go like crazy. It doesn't double or like that. Yeah, that's what I find in the simulations with very large beta.
All right. I think we have a couple more questions, and then we'll go back to Neil's next question. So we have a question from Venkat. If you want to unmute and ask it.
Yes. I have a small question about alpha beta interplay. You fixed alpha in your simulations, and I'm just curious how sensitive is the gap to the alpha beta interplay in your simulations?
Oh, yeah, again, this is work in progress, and I just used one alpha value, at least for now. So yeah, unfortunately, I don't have an answer for that.
All right. Next question from Enrique.
Hey, Jaehan, really nice talk, really interesting stuff. I have a question about your TW Hydra model. So in Richard's paper in 2019, you also found spiral arms in the brightness temperature. So I was wondering if you are also able to reproduce those. And then also related to question, did you try another position for the planet? Because as you know, there's this blob that was detected at 50 AU. So I was wondering if that could also reproduce the spiral arms.
Yeah, those are really great question. Yeah, so one thing really interesting, I have my Zoom chat on top of my screen, but anyways, let me see if I can play this again. No, sorry about that. Okay, yeah. Do you see my chat window, by the way, or are you seeing?
No, we
okay,
don't.
that's good. Yeah, so you cannot really see here, but let me see if I have that plot in my backup slide. No, I don't. Yeah, so one of the things very interesting is that when you look at the density and temperature and you compare the location of the spiral, say spiral arm, or where they peak at, right, in azimuth at a given radius, they have a shift with respect to the vertical velocity, 90-degree shift. And you can think of it as a standing wave. When you have a string and you make a perturbation, right? Then the velocity and the position, they have 90-degree shift. And that's exactly what is in here. Now, if we look at the exact location of the temperature spiral and velocity spiral, if I remember this correctly, we see some shift in azimuth between those two spirals, but yeah, I haven't actually checked that for using my simulation, but yeah, I will do that. And the other planet locations, which one were you specifically talking about? The one where a continuum peak is found in around 30 AU, or?
Yeah, well, I was wondering if you, no, I was wondering if you tried any other position, but specifically that one, yeah, the continuum blob that was detected at 50 AU, which some people said could, well, they claim in the paper they could be a planet or could be another thing, a vortex or something like that.
Yeah, no, I haven't done that, but I believe that that planet has to be much lower than the one I used here. This one I assumed 0.5 Jupiter masses, and that one at 32 AU, that is still embedded in the millimeter continuum disk, and it didn't really open a huge gap in continuum. So I believe if it's a planet, it has to be much lower mass planet, perhaps Neptune-ish, I would say, planet, and it, well, in theory, if you put a planet at 30 AU, in this case here, right, you can expect that the Lindeblum spiral from that planet will decrease, and at 90-ish AU, you can expect that you have very small pitch angle. But then the question would be then, why do we not see all those spirals near 30 AU? Because you'd expect that near the planet, you'd generate much stronger perturbations than further away. So that's one of the reasons why I prefer to have planet at this location than explain these structures with a planet at 30 AU.
All right.
That makes
sense.
Thanks.
We have a few more. Oh, yeah. Sorry. We have a few more questions, but I know some of you have to leave soon. So I just wanted to announce quickly before we go on that many of you will be setting your clocks back an hour before the next Origin seminar, but those of us in Arizona will not. So please double check your local time before tuning in for the next meeting. All right. So back to Neil Turner in the chat, who asks, isn't the cooling time much longer than the interval between shock passages so that the gas remains hot?
Yeah, that's true. Yeah, shock passage time can be much shorter than the cooling time scale if you choose really large beta value. So that's partly why the disk temperature does not cool down all the way to the initial condition. But I should say that the planet mass, what I used here is 2 Jupiter masses. 2 Jupiter masses, it might sound very large, but also the stellar mass here is 2 solar masses. So you can think of it as a Jupiter mass orbiting around a solar star, even though it's 2 Jupiter masses.
All right. Question from Andrea.
Hi, Jaehan. Thank you for the nice talk. I have a question that goes back to Neil's comment about stellar irradiation and what you show about TW Audra. So in the paper that Neil mentioned, we show that you can get, shadowing can create gaps in scattered light. So a gap in scattered light is not necessarily means that you have a gap in the density.
Yeah.
And another effect of shadowing is that you change the temperature, the radial temperature profile, because the shadows are colder. The region in the shadow part is colder. And if you change the temperature in the midplane, you can change the pressure support, and that could lead also to variation in the rotational velocity. So I wonder whether that could somehow also create this kind of feature you see in your velocity plot here.
Yeah, but well, yeah, I fully agree that shadow can change the underlying temperature structure. But if you forget about spiders for now, right? If you look at this image, right, it's pretty much axisymmetric, right? So if something is creating, whether it's planet or something else, right? If it's annular structure, symmetric structure, you don't necessarily expect to see spirals in shadow, right? Or yeah, temperature. It will be more or less, yeah, circular, concentric if it's stellar irradiation. I don't know if that answers your question.
Yeah, thank you.
All right, Andrew/Caitlin.
Andrew again, thanks. So I'm trying to, just because I haven't thought about it very much, trying to understand the vertical velocities, VZs, that you're showing. So do these apply everywhere? Do they just apply like to the front half of the disk? So like, is there a symmetry about the midplane, or is it going through the midplane?
Yeah, it's symmetric. So you expect to upward on one side and downward. So it's symmetric against the midplane, and this plot might help you. Yeah. So what I plotted here is, this is a lot of panels, but at different locations in height, midplane, this is 1 scale height, 3 scale heights, density, vertical velocity. Yeah. So if you look at vertical velocity, buoyancy resonance is pretty strong, and it's stronger than the Lindeblum spiral. Actually, you can see here Lindeblum spiral in this case. Whereas if you look at the radial velocity, for example, Lindeblad resonance is much stronger than buoyancy resonances. So it depends on where in the disk you look at. For example, if you look at the middle plane, because of the symmetry, you don't expect to see buoyancy resonances. So it depends on the disk and disk geometry. And I think TW Hydra is the most favorable to observe this buoyancy resonance because of the face-on geometry.
Great. Yeah, no, thanks a lot. And then I guess maybe if you had an optically thin disk, would things then get confusing because you'd have both components of vertical velocity?
You mean from upper side and lower side of the disk? Yeah, in theory, but then the disk has to be, I think, really, really optically thin, thinner than C18O. So.
Great, thanks.
Yeah.
All right, another question from Neil Turner. What relationship do you advocate between line of sight motions measured by ALMA spectroscopy and the angular momentum transport parameter alpha? For example, what relationship should we use if the AM transport comes from one of the currently popular magnetocentrifugal disk winds?
Yeah, that's a hard question to answer. I'm not advocating that what we see with ALMA. So what we do is with ALMA observation is not measuring angular momentum transport, right? We are measuring non-thermal random motion, if it exists at all, right, of the disk gas. That may or may not necessarily be the same thing as angular momentum transport, right? Even if there's some non-zero, non-thermal motion, turbulent motion, right? The other thing I'd like to talk about is that turbulence, it can be anisotropic. So you can think of this as random motion along, vertical direction or along radial or azimuthal direction. Well, some turbulence can be isotropic, but hydrodynamic simulations, hydrodynamic instability, for example, vertical shear instability, we know that the turbulence is not isotropic. So depending on, the geometry of the disk, again, what you measure may not necessarily be the intrinsic level of turbulence you get. So I'd like to point out those two things. And yeah, magnetocentrifugal disk winds. Yeah, I don't have an answer for that, to be honest. Yeah, I see another question from Neil. Give me 1 second. Yeah, that's an interesting question. I haven't done any calculation about that. Transit times for parcels of gas entering a wind. What I can tell is, well, those wind, if I remember this correctly, they will launch at upper regions of the disk. I don't know exact number, but that has to be 3, 4, 5 scale heights, right? So if you are sitting on that far away from the disk middle plane, yes, it is possible that before you cool down, you can meet a disk wind. But if you are interested in, say, within 3 scale heights, I would say, and then I don't think you will meet those MHD winds at that vertical locations. I don't know, Neil, you can comment on that, comment on my argument. Although,
So we are over time at this point. So I suggest we stop there and the two of you can hang around or move the conversation offline. But for everyone else, I would like to invite you to unmute and thank Jaehan for a very interesting talk.
Thank you so much.